So, believe it or not, I'm in Reykjavik, Iceland, at the marina near the Harpa Center, a concert center, where the European Astrobiology Institute's Beacon 2025 is being held. And I'm outside in on a cloudy, drizzly day, and what should be summer, with Adam Valantinas, a planetary scientist at Brown University in the U.S. Brown has a long history of geoscience, both here on Earth and elsewhere. And Adam is doing research on Mars. And why Iceland? You're also going to be doing a field trip after the conference. Tell us about that and who's funding it and what you're going to be doing.
Yeah, so I'd like to thank my funders, American Philosophical Society, specifically the Baruch Bloomberg Grant for Astrobiology Research, which funded my trip here to Beacon, the conference on astrobiology, and then fieldwork right after. So I'll be in the Icelandic highlands for a week, sampling iron oxide minerals in every kind of aqueous environment, from cold springs to hot springs and rivers there, and the idea is to use Iceland as an analog for processes that could have happened on ancient Mars, and by that we can understand the climate and the habitability and the possibility of life in these type of environments on ancient Mars.
And why is Iceland better than anywhere else?
Well, Iceland is a volcanic island. It has basalt as a kind of the bedrock material, and Mars is also a basaltic planet in nature. So the weathering of the basalts leads to secondary minerals on Iceland, and similar secondary minerals are observed as well on Mars.
And you gave a fascinating talk, which we have been discussing. You'd been doing research on the impact crater, Jezero Crater, where the NASA's Perseverance rover is currently on the rim. So tell us the gist of your paper that you gave.
Yeah, so we employed observations from orbit using spacecraft data to understand the composition of the Jezero Crater rim, and we also did numerical simulations, so using computer models to understand how the movement, the materials moved post-impact and where they were deposited, what was the temperature of these rocks and the pressure conditions, in order to understand if the materials and the minerals there could have been preserved and how they were produced. And basically in the end we saw that there are a lot of secondary minerals, lots of minerals that have been produced by liquid water, and those minerals and rocks are very old. They come from around 3.8 maybe billion years ago in the Martian history, and that's the time when there was liquid water on the surface, and possibly life could have maybe existed, so the environment was potentially habitable.
Let's talk about the samples that Perseverance has collected. You said there was a great diversity in the samples it's collected, which is indicative of what?
So the diversity in samples indicates that the environment was potentially habitable because life needs different materials, different minerals, different conditions, but as well the diversity of these minerals, which hint to also a very complex and environment involving liquid water. So that's basically the diversity of samples hints to habitable environment on ancient Mars.
And the problem right now is, as you well know, the Mars sample return mission is in doubt, correct? I mean, I think you have your ear on the to the ground on this one. To my knowledge, the sample return is not funded at this point.
So far, it looks like Mars sample return might be canceled. I mean, this is not officially yet now decided. I think Congress is going to look at the budget proposal for NASA, but so far the Mars sample return looks like it could be canceled. That's correct.
But the serendipity is, even though you have something like there have been 41 samples taken, some of them have been placed on the ground in case the rover doesn't make it back to the landing site, so we can retrieve some samples. But you said the most interesting samples were already on the rover. But serendipitously, if the sample return is delayed for several years, the rover can still function. And you said that it could be a blessing in disguise, even though we want those samples back as quickly as possible. That's true, because you could use the rover to explore beyond the crater rim or south. Now, let's take the crater rim, beyond the crater rim. Why would that be interesting for us?
So beyond the crater rim, there is this area called Nili Planum. It's basically a flat terrain that contains a lot of volcanic minerals, which can, help us understand the nature and origin of these volcanic minerals on Jezero Crater floor, but also the Jezero Crater rim. If you go south, maybe perhaps 30 kilometers south, there are a lot of alteration minerals, a lot of minerals that could have been formed by hydrothermal activity. So heat and water permeating through fractures in rocks, and these type of environments and rocks, they represent perhaps quite different environments from the one that the Perseverance rover explored on the crater floor, where you have a lake environment and deltaic deposits. So going south, basically, not only you have hydrothermal minerals, but those rocks are potentially even older than the Jezero impact itself. So they could be 4.1 billion years old, and so the likelihood and potential for habitable environment is perhaps even greater if the Perseverance team is allowed and decides to actually drive and explore south.
So last question, what has surprised you most in your research on Jezero Crater?
What surprised me the most is the diversity of mineral types and the diversity of rocks that is specifically observed in the Jezero Rim, and that kind of, as I mentioned before, it's basically suggests that the environment was habitable. It contained liquid water, and the rocks there, they were weathered and chemically altered by interactions with liquid water.
So thanks so much, Adam, for taking the time today. We look forward to hearing more from your research.
Thank you so much. Yeah.